Hello everyone, and thank you for coming to listen to the presentations today. Also, thank you to Josh for organising this event. To start off, my name is Emily Canda. I'm a PhD candidate from the University of Technology, Sydney, and today my presentation is about exploring Australian clays as a supplementary cementitious material, also known as a SEM. So why would I be talking about this today? There is an issue with concrete. Concrete is the most used construction material in the world, and for such a used material, it only makes up to 8% of the world's total emissions, which is actually not that significant compared to other construction materials, considering how much concrete is used around the world. However, we could always do better, and we need to do better. We need to avoid such events like the Australian bushfires in 2020. The majority of these emissions are produced during the process of calcinating at 1450 degrees Celsius to manufacture clinker, which creates cement. Therefore, the most efficient way to cut CO2 is to replace portions of cement with alternative supplementary cementitious materials. At this stage, SEMs have been used for decades in various markets and are quite common in Australia. The most commonly used SEM is fly ash and slag. Whilst fly ash has worked well as an SEM over the past decade, it is fast declining. This is due to coal-driven plants using more sustainable methods of powering the plant. It is also predicted that the cost of cement will increase due to the availability of resources becoming dire. This means that countries that are already struggling to fund their infrastructure will struggle more. However, an SEM that has recently gained attraction is a promising technology and a solution to sustainable and readily available concrete. This material is clay. For those of you who don't know about LC3, limestone calcine clay, I will start from the start. The clay mineral I am referring to is kaolinite. Kaolinite is also known as China clay and is typically white in colour. The kaolinite is calcined, another term for burnt, and it is transformed into metakaolin, which acts as a natural pozzolan. Kaolinite, however, is very expensive, and the mines in which this pure kaolinite use this products to produce products such as paper, ceramic, paints, etc. Therefore, high-quality kaolinite pits are sought after, and they're quite high in demand. However, prior research suggests only 40% of the clay needs to consist of kaolinite in order to create a concrete technology that can outperform traditional GP cement. This brings us to calcined clay, which is a term used for clay consisting of various minerals which has been calcined. So 73% of the world's crust consists of clay. It is everywhere. With the knowing that clay only needs to consist of 40% kaolinite brings a world of opportunity in terms of creating an SEM anywhere in the world. As seen through this map, the yellow, pinks, and pale greens represent the availability of kaolinite. The clay does not need to be pure, which means that low-quality clays can be used. The dehydroxylation of kaolinite to metakaolin is usually around 550 to 750 degrees Celsius. Therefore, the calcination temperature is around 650 to 850 degrees Celsius, depending on the chemistry of the clay, which is less than half the required temperature in order to calcine clinker. LC3 is not a new technology and has been worked on countlessly. The design for this study utilizing the traditional 30% replacement, which is 20% calcined clay, 10% limestone, and 70% GP, which means 30% of traditional GP binder is replaced, creating a more sustainable material. The first step in producing this technology is finding the clay. After doing an initial investigation of clay pits in Australia, it was understood that the opportunity to find clay was endless, and therefore there was a prospect of choosing a site based on economic feasibility. Going out to the various sites looked very similar to this image. Piles and piles of clay that were stockpiled as they were overburdened at sites that were already extracting the clay, not necessarily using it, but stockpiling it. In this case, this site used their clay as a barrier, as a means to find use for it. The criteria in selecting the sites to further investigate was simple. We targeted sites within an 80-kilometre radius of a kiln. It had to already be extracted, and large quantities had to be available. Even though there was a rigorous criteria, 9 sites actually fit into this rubric. From this, 46 samples were collected in total. Around 5 samples were taken per site. Most of the sites I was able to access and take a representation of the metre square for sampling. The sites I couldn't access due to COVID, strict instructions were sent to the person to collect the samples. The samples were then sent to UTS Tech Lab, in which they were analysed for kaolinite content using the EPFL tangent method. This method was selected as it was quick, straightforward, and minimal knowledge was needed in order to conduct the test. From the EPFL tangent method, it was found that 50% of the samples contained kaolinite content above 25%. From the 9 sites, 4 sites were selected to undergo further testing. If we look at the total average kaolinite content of all the sites, All of them actually contain some level of kaolinite. The kaolinite content was then also confirmed through analysis of X-ray diffraction and thermogravimetric analysis. After understanding more about the various Australian clays through XRD and TGA analysis, the project methodology of exploring Australian clays as an SEM became quite clear. Firstly, we had to collect the Australian clay. And then we had to obviously understand the optimal calcination temperature, then see how it performs in a simple mortar mix. At the time of this project, COVID was occurring and there was no companies in Australia to calcine or mill the material in bulk. Therefore, a production line was created in order to calcine the clays. This methodology of creating these clays took over a year with lots of help from various different people. The process required the clay to be dried enough to jaw crush, then calcined at 650 degrees Celsius, then milled at 100 grams at a time to ensure the PSD was the same and was consistently met. At the end of this process, we were able to access around 20 kilos of the Australian calcined clay to experiment with. In the end, we had 8 materials to experiment with. So at first, we have our reference materials, which are fly ash and GP. We then have the imported calcined clays, FCC and ICC, which are characterised by Ju Nguyen in our research team. And then the Australian calcined clays, in which were a representation of the 4 selected sites, labelled ACC, BCC, CCC, and DCC. During the production of the calcined clays, it was important to understand if these Australian clays would even be feasible, as the producing of the calcined clays was difficult and very time-consuming. So therefore, the XRF was conducted and confirmed that the Australian clays were feasible as they fit within the desired range of a natural pozzolan and sat between the reference calcined clays. This further proved feasibility and the production of producing the calcined clays continued. Once enough clay was produced, mortars were created with the various binder designs. The first reference being GP was made up of 100% GP, the second reference being fly ash, which consisted of 30% fly ash and 70% GP. Then the LC3 mixes, which comprised of 70% GP, 20% calcined clay, and 10% limestone. The mortar test followed ASTM C305-20, which meant a water to binder ratio had to be redesigned. In this case, a water to binder ratio of 0.43 was used. When we look at the 28-day compression results of these mortars, most of the LC3 mixes are comparable with GP. All LC3 mixes outperform fly ash, further proving feasibility of LC3. The metakaolin content of the imported calcined clays are unknown. However, after XRD quantification of the clays, it was found that ICC consisted of 77.9% amorphous phase and FCC consisted of 70.6% amorphous phase. When we look at the Australian clays, ACC had a much higher metakaolin content than BCC, but BCC had a much higher amorphous phase content, which led to very similar results at 28 days. This demonstrates that even if the clay may not have a high amount of kaolinite, it is worth understanding the clay and its amorphous phase when calcined, as it could be a potential SEM. The significance that LC brings is fundamental to the growth of the concrete industry and is a solution to more sustainable concrete. By utilising LC3, not only is less CO2 produced, it gives access to produce affordable and a sustainable product without sacrificing the strength of concrete, whilst also utilising a waste product. This research is a starting point improving LC3 viability here in Australia. However, continuous research is needed to continue the building case study. I would like to thank the UTS Boral Centre for Sustainable Building and UTS Tech Lab for supporting this research. Special thanks to my wonderful supervisors and the UTS Tech Lab staff. Thank you for listening. I hope you consider LC3 in your future projects.